Hi, my name is Brian Caffo, and this is Mathematical Biostatistics Bootcamp, Lecture 4 on two-sample binomial tests. Okay, in this lecture, we're going to talk about the score statistic, which is a specific two-sample binomial test that will serve as motivation for creating a confidence interval as well. We'll talk about how you can do exact test for two binomial proportions, and then we'll talk about comparing two binomial proportions, and then we'll go over a little bit about Bayesian and likelihood methods for comparing binomial proportions. We'll actually spend quite a bit of time on binomial proportions because later on we'll also talk about relative risks and odds ratios and that sort of thing. Okay, so let's put some context on this. So imagine a randomized trial where there was 40 subjects and 20 each were randomized to two drugs. And the two drugs had the same active ingredients, but let's assume they had different expedients. That ways in which the drugs were delivered. One, let's just say one was a capsule and one was a different kind of pill. Okay. So consider counting the number of side effects for each drug among the 40 people. So here we have a table where there's 40 total people, 20 in drug A, 20 in drug B. So this margin is fixed, 20 and 20, that margin is fixed. And then 11 from drug A received side effects, and then 9 didn't, and then 5 from drug B had side effects, and 15 didn't. So on face value, there seems to be a greater propensity for side effects from drug A than from drug B. And what we'd like to do is to do a test of whether or not the side effects are, the propensity for side effects is the same within the two drugs. And there's a lot of different ways we could formulate this problem, even from this simple data set. And we'll talk about some of the ways to do that. But for right now, let's just start with talking about score test. So the score test should seem fairly familiar to you because it's just going to be constructed in the same way that the ordinary test is. The sort of ordinary z-tests are constructed in the way that we had before. So let's consider a single binomial proportion, not two binomial proportions, but a single binomial proportion, and later on in the lecture we'll consider two binomial proportions. So imagine only looking at drug A and saying, well, let's test whether or not drug A has a specific population proportion of side effects. So we want to test H naught P equal to P naught, and so our obvious estimate of P naught is P hat, the sample proportion of side effects. Okay, so our obvious metric of the discrepancy between P hat and P naught would be the difference, or maybe we could do a log ratio or something like that. But for right now, let's do the difference. Okay. But in order to compare this to a statistical distribution, let's normalize it by the variance of P hat. Well, the variance of P hat is P times 1 minus P over N, and under the null hypothesis, that's P naught times 1 minus P naught over N. So the standard error is the square root of that. And notice that we're plugging in the P naught under the null hypothesis, not plugging in P hat, which would give us the estimated standard error that we used, for example, in the construction of the confidence interval. So at any rate, this test, when you plug in P naught in the denominator here, performs a little bit better than the so-called Wald test, where in the denominator, rather than plugging in P naught, we plug in P hat. So remember how we can invert this test statistic to perform to create a confidence interval, and we can, of course, we can use the test statistic to just perform the test. So I should have said this on the previous slide, but that z statistic you compare to quantiles from the standard normal distribution. the upper alpha over 2th quantile if you're doing a two-sided test, the upper alpha over 2 quantile if you're doing a one-sided greater than test, the upper alpha quantile if you're doing a one-sided test where the alternative is greater than p naught, and the alpha quantile if you're doing a one-sided test where you're testing p less than p naught. Okay, so and this should be obvious to you at this point in the class, how you would take a z statistic and then use it to perform a test. And then, of course, we've already talked at length in other settings, for example, in inverting the t-test and the standard z interval, on how we can invert a confidence interval and invert a hypothesis test and create a confidence interval, namely, calculate those values of p naught for which we'd fail to reject. If we invert the Wald test, we get the Wald confidence interval, p hat plus or minus z 1 minus alpha over 2 square root p hat 1 minus p hat over n. And if we invert the score test, we get a so-called score interval, which is a lot more complicated. We get p hat times this quantity plus 1/2 times this quantity plus and minus our normal quantile, our upper alpha over 2 normal quantile, and then this standard error formula. I want to point out one thing about this is not a numerator here, by the way. This is this quantity p hat times this thing plus 1/2 times this thing, and then I ran out of space, so then on the next line I put plus or minus the normal quantile times the standard error. So this is p hat times n over n plus z squared, and then plus 1/2 times z squared over n plus z squared. So look at these two factors, n over n plus z squared and z squared over n plus z squared. They add up to 1. So they're two proportions that add up add up to 1. So in other words, a point on the two-dimensional simplex is what you might say in mathematical parlance. But what's important is as n gets very big, this first term gets very big, and p hat dominates. If n is small, then this term in front of the 1/2 gets a little bit bigger, and well, the 1/2 probably hopefully doesn't dominate, but there's more greater fraction placed on the 1/2. And just to give you context, the z 1 minus alpha over 2, well, z, that's usually going to be around 2, so this is about 4. So it's about n over n plus 4 plus 1/2, 4 over n plus 4. At any rate, and as n gets very large, it just becomes very similar to the Wald interval. So what this does is it takes p hat and it shrinks it towards 1/2. And that turns out to be a good thing to do, because the binomial confidence interval, you don't want it centered exactly at p hat, because the binomial distribution as p hat is further away from 1/2 gets more asymmetric, it gets more skewed, and because of that you don't want that point right in the middle. At any rate, so we talked previously about confidence intervals for binomial proportions, and plugging in z1 minus alpha over 2 equal to 2 yields the so-called Agresti-Coull interval that we talked about before. So this is actually the motivation for the Agresti-Coull interval, is that most people do 95% intervals, and if we take our 1.96 and just round it up to 2, and plug it into the score interval, we get exactly the Agresti-Coull interval. Okay, so let's do our example. In our previous example, consider testing whether or not drug A's percentage of subjects with side effects is greater than 10%. So I made up 10%. So let's assume that the FDA gets really mad for this kind of drug if you have more than 10% prevalence of side effects. So H naught PA is equal to 0.1 versus HA PA greater than 1, where PA is the population proportion of side effects for drug A. And then our p hat is 11 over 20, which is 0.55. Our test statistic is 0.55 minus 0.1 divided by square root. Remember to plug in the p naught from the null hypothesis. 0.1 times 0.9 divided by 20, you get 6.7. We reject the p-value. We reject, our critical value is going to be, for a one-sided test, is going to be about 1.65. or a two-sided test, if it would be about 2. Either way, 6.7 is going to be bigger than it. And then our p-value, the probability of getting a z bigger than 6.7, is of course nearly around 0. 7 standard deviations away from 0 for a standard normal is quite far out in the tails. Remember that 3 standard deviations covered the majority of the distribution. And then if we were doing a two-sided test, remember that we would double this p-value. Okay, now let's discuss this problem a little bit. So what do we have to do to get this to work? So mechanically, I hope you find this easy, but let's talk a little bit about the thinking of this. So we're postulating that the number of side effects out of 20 is a binomial trial. Well, that implicit in that is the idea that then we have IID data. Every person is independent and identically distributed draw from a population. So we're using those assumptions, the IID assumptions, to create the idea of a population, superpopulation that has a prevalence of side effects of PA. Of course, we cannot, in general, you can't know that unless you're actually in a setting where people are going to great pains to actually sample independently from the population they're interested in, which is usually not the case. In general, the sample is, what you're doing is you're doing a statistical model where you're hoping that the people are a representative sample. You're hoping that there's no crossover of side effects. So let's suppose some of the people receiving the drug are friends or in the same family or in the same neighborhood or something like that, that there's no reason that if one person gets side effects that it's more likely for anyone else around them to get side effects who also receive the drug. So no interference is what they would call that. And so our IID model is what's giving us here this idea of a population proportion, and then we're testing relative to that proportion. But it's good, I think, whenever you're doing these kinds of tests to actually think about what you're modeling is random and what your population model is that you're trying to do it, because modeling is the calculations here are very simple, right? I hope we all agree that the calculations are very simple. But the principles, the idea of how the modeling is going is a lot more delicate and actually on a lot more shaky ground. So that's why it's a good idea to always sort of think through your modeling assumptions and what they imply for your actual hypothesis. So just to give you an example, let's assume that our sample of people are all people who are professional drug takers for pharmaceutical companies, sort of professional guinea pigs. Whenever a drug company says, "Oh, well, we want to test out this headache medication," they sign up. And there are people who do this, of course, right? You can make maybe not a tremendous living doing it, but the drug companies, of course, pay people for their time to test out these sorts of drugs. Then it would be hard to declare that population IID draw from the general population, because this is a very, very different sort of people. They probably adhere to their medication schedule very precisely, and other things like that. They're probably very good takers of medications. They probably do the instructions quite well. They know, and so on. So at any rate, my larger point being is that when you get this number 6.7, which is very easy to obtain, think about what it means in the context of the model that you've used. And in this case, the model is seemingly very benign, but the big part of the model is the IID draw from a population. Think about what that means in the context of the problem that you're studying. Okay. So in the previous slide, our assumptions depended on having a large enough sample for the central limit theorem to be applicable. We can't actually do an exact binomial test, which by exact I mean the calculation utilizes the binomial distribution rather than the asymptotic distribution of the normalized sample proportion. So in this case, the event of getting, so we observed 11 people with side effects in the sample. we're testing greater than, that our sample proportion is greater than something else. So the probability of getting evidence as or more extreme than we obtained would be the probability of getting more people than we observed, which is 11 side effects. So this is the probability of XA, which is the count of the number of people with side effects for drug A, being bigger than or equal to 11. That's the sum from 11 to 20 of the binomial proportion. And then you might ask, well, where does the null hypothesis come in? Where does the fact that we're under the null hypothesis that P naught is 0.1? Well, right here, so it's 0.1 to the x, 0.9, which is 1 minus 0.1, to the 20 minus x. So in other words, this calculation, the probability of getting more than 11 people with side effects out of 20, is done under the null hypothesis that P naught is 10%. So this is the probability of getting evidence as or more extreme in favor of the alternative, with the probability being calculated under the null hypothesis. So this is a p-value. If you do this calculation, the probability of getting 11 or more out of 20 with a probability of 0.1, if you do that calculation, that probability is around 0. There's very little contribution of these numbers are quite small. And you can do this in R very easily. Just p binom 10, 20, 0.1, lower dot tail equals false. Now, I just want to point out the small little detail here. If we did p binom and didn't have this lower dot tail equals false, if we had lower dot tail equals true or omitted it because the default value is true, then it's going to calculate 10, the probability of 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. If we do p binom lower dot tail equals false, in other words, it wants to calculate the greater than probability, it does strictly greater than. So if you do lower dot tail equals true, it does less than or equal to, so includes 10. If you do greater than, if you do lower dot tail equals false, hence you want greater than, it does a strictly greater than, so it starts at 11. So if you put p binom 10, 20, 0.1, lower dot tail equals false, it's going to calculate the probability of 11 plus 12 plus 13 plus 14 plus 15 plus 16 plus 17 plus 18 plus 19 plus 20. Okay, so in other words, p binom 10, 20, 0.1, lower dot tail equals true, that number, plus p binom 10, 20, 0.1, lower dot tail equals false, those two numbers add up to 1. 10 is only included in the instance where lower dot tail equals true. In the instance where lower dot tail equals false, it goes above 10 to 11 and higher. Anyway, it's a small point, but you get the wrong answer if you don't do that. And then if you want to avoid this discussion, you could just do binom.test and say, well, we had 11 successes out of 20 trials, and we want to test the hypothesis that it's 0.1, and I want my alternative to be greater, and binom.test does it. Binom.test is maybe a little bit nicer to use because it actually it actually does gives you the exact confidence interval as well. Okay. So one of the reasons this test is called exact is that unlike the asymptotic error rates, where the alpha that we use to get the normal quantile is an approximate error rate for the test. So if you perform a 5% level asymptotic test, the alpha level is not necessarily 5%. It might and there's been work to show that in some cases it can be substantially higher than 5%. On the other hand, this exact test, this guarantees that the alpha level is, let's say you pick alpha equal to 0.05, it guarantees that the alpha level is 5% or lower. The problem being or lower is that it's exact but conservative, so it's 5% or lower. So in some cases with very small sample sizes, the exact level can be much less than the observed level, than the desired level. And then, for two-sided tests, what I'm going to suggest is calculate the two one-sided p-values. It should be obvious which one is going to be the smaller one, and then double it. And that just kind of follows our rule we've been using in normal tests, and this is good enough. There are maybe slightly better procedures, but they change the numbers only a little bit. So given that we can do a two-sided test, either by this way or maybe by better ways, we could calculate every value of p nons, let's say by a grid search, for which we would fail to reject the null hypothesis in our two-sided test, and that would yield a confidence interval, and that confidence interval would have an exact coverage rate. So it would have coverage, if you did a 5% test, it would have coverage 95% or higher. That's right. So all these things are slightly conservative, so it would be 95%, maybe much higher, maybe 97% if it's a very small sample size. And this interval is given a name. It's called the Klopper-Pearson interval. The benefit of it is it guarantees your coverage rate. You get coverage 95% or better, or higher. The problem is that in the event that it's or higher, you've potentially unnecessarily widened the interval, right? Because if you want higher coverage, you're generally going to get a wider interval. So there's no such thing as a free lunch. And exact intervals fall under that category just as well as everything else, in that they do guarantee your error rates, but then they have this tendency to be conservative. Wider intervals, being a little bit less likely to reject the null hypothesis, are the consequences of using them. On the other hand, you do get the assurance that the error rate is exactly adhered to given your assumptions. I just wanted to show a picture from an American statistician paper that I was involved in based on earlier work by Agresti and Coull. And here, what we did is we compared the coverage rate of the Wald interval versus the approximate Wald interval obtained by using the inverting the score test, and just simply plugging in 2 rather than 1.96. And what you see in these top lines is that the jagged, they're jagged because of the discreteness of the binomial distribution. Here we show, let's just look at this top row for 95%. Okay. What you can see is that this solid line, the Agresti-Coull interval, it hovers right around 95%. Sometimes it's a little low, sometimes a little high, but it still hovers right around. The Wald interval can be quite a bit off. Now this is a small sample size, so that there's no reason to believe the asymptotics have kicked in and done very well. But even if you get up to, say, a sample of size 20, the closer the true value of p is to 0 and 1, you can get coverage that is very low, 70 below. Here I think it's truncated at 70%, but it dips down and touches 0 at 0 and touches 0 at 1. So the point being that switching away from this Wald interval where you put p in for the confidence interval, where you put p hat in the standard error calculation, to the Agresti-Coull interval where it's a simple fix, really improves performance quite a bit at no conceptual or computational cost. So that's just the point I'm trying to make here, and it relates to this discussion of it's basically saying that the score interval is performing a lot better than the Wald interval in this case, and that tends to be a general rule of thumb. Okay, so now let's actually get to comparing two proportions rather than simply looking at one proportion. So we want to test whether the side effects is the same in the two groups or different. So imagine if A is some new formulation and B is the standard, and you want to test whether or not the new formulation has more side effects than the standard. So in general, for 2x2 tables, I'm going to use the following notation. I'm going to have x, n1 minus x, and n1 plus y, and n2 minus y, and n2 plus. And then if I need to, I'll refer to the 4 cells, indexing them by their matrix coordinates n11, n12, n21, n22. I'll call n1 the right margin, n2 the right, n1 the right top margin, n2 the right bottom margin. But if in the case that I'm referring to both margins, I'll say n1 plus n2 plus, n plus 1, and n plus 2 for the respective margins. In other words, just summing, the notation meaning summing over that index. Okay, so now let's do a score test type test of a hypothesis that P1 equals P2. So our null hypothesis is H naught P1 equals P2 versus not equal to, greater than, or less than. And then the score test for this null hypothesis, our numerator is P1 minus P1 hat minus P2 hat, the sample proportion in group 1 minus the sample proportion in group 2. And then if we were assuming that this difference was a constant other than 0, we would put that in the numerator here, the null hypothesis difference. But typically, the null hypothesis is that they're equal. So there's minus 0 here, the hypothesized null value of the difference. So we can just omit that. And then in the denominator, under the hypothesis that P1 equals P2, then the variance of P1 hat minus P2 hat is P times 1 minus P quantity times 1 over N1 plus 1 over N2, where P is the common proportion P1 equal to P2. So under the null hypothesis, we need an estimated version of that if we're going to actually get a number here that we can use compared to a normal quantile. So we need a value of P to plug in there. So we say plug in P hat. If under the null hypothesis the sample proportions are identical, then group A is a bunch of IID draws, IID Bernoulli draws from group 1. Group B is a bunch of IID Bernoulli draws from group 2, but they have the same proportion, so we really just have N1 plus N2 Bernoulli draws, and our estimate of the proportion would simply be the total number of events. So that P hat is X plus Y over N1 plus N2, and that is exactly the MLE for P, the common proportion under the null hypothesis that the two proportions are equal. So we plug that into the denominator, P hat times 1 minus P hat, and then we get our test statistic, which is again just estimate minus hypothesized value divided by the standard error. And then this statistic is normally distributed under the null hypothesis for large N, standard normally distributed under the null hypothesis for large N1 and N2. So if we want to invert this to create a confidence interval, well, we don't have a closed form like we do in the score test for a single proportion. The Wald interval is P1 hat minus P2 hat, and then it doesn't utilize the fact that under the null hypothesis the proportions are equal, so then you just have a separate P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2 in the denominator, square root the whole thing. And you can of course invert that to get a confidence interval, P1 hat minus P2 hat plus or minus Z 1 minus alpha 2 times the square root of the standard error. By the way, do you see why you can't invert the score test? The reason being that if you change the denominator was explicitly calculated under the specific null hypothesis that P1 equals P2. Here in this test statistic, if we were to have a different null that P1 minus P2 wasn't just equal to 0 but was equal to some other value, we would add that in the numerator and then the denominator wouldn't change, whereas in our score test we wouldn't have any way to adapt that denominator, and that's or no immediate way to adapt the denominator, and that's why you have to use some programming to get the confidence interval from that one. But this one, the Wald test, we can invert very easily, and we get an interval that should be fairly familiar to us. P1 hat minus P2 hat plus or minus the normal quantile times the square root of the standard error. That's the so-called Wald interval. It's very easy to calculate, and it's taught in nearly every statistics textbook. So this performs poorly. This Wald interval performs poorly, and it's relative to the score interval and test. The Wald test and the Wald interval perform relatively poorly, but their decrease in performance is less so in the one sample case. In the one sample case, there's a huge decrease in performance, but the subtraction of the two proportions, subtracting two things tend to make them more normally distributed, so it helps a little bit. and the decrease in performance for the Wald interval isn't anywhere near as bad as it is in the single proportion case. So for testing, I would just say always use the score test. That's easy. For intervals, inverting the score test is hard, and it's not in standard software. So our simple fix that we propose in an American statistician paper is to add one success and one failure in each group. So calculate P1 tilde, which is x1 plus x plus 1 over n1 plus 2, n1 tilde, which is n1 plus 2, P2 tilde, which is y plus 1 over n2 plus 2, and n2 tilde, which is n2 plus 2. So this is exactly taking this 2 by 2 table that has the successes and failures for each group and adding one to every cell. That's exactly what this is. And then just treat that as if it's the data and construct a Wald interval. And this interval, it doesn't approximate the score interval like in the Agresti Coull interval, but it does perform better than the Wald interval. And I'll have a slide in a second to show you this. Okay, so let's just perform the test, the score test, test whether or not the proportion of side effects is the same for the two drugs. PA hat is 0.55, PB hat is 5 over 20, which is 0.25. P hat, the common proportion, is 16 over 40, 11 plus 5 over 20 plus 20, which is 0.4. So our test statistic is 0.55 minus 0.25 over 0.4 times 0.6 times square root 2 over 20. Square root the whole thing. Anyway, you can plug in the formula, you get 1.61, and then we fail to reject H naught at the 5% level. In other words, you compare with 1.96 for a two-sided test. The two-sided p-value, calculate the probability that the absolute value of a standard normal is bigger than 1.61, which is that the positive part of a normal is bigger than 1.61, plus the probability that the negative part of a normal is below negative 1.61. That's, I guess, 0.055 in either tail. So we fail to reject. There's our p-value. And so hopefully everyone can do this calculation very easily at this point in the class. Okay, so here's the same picture as before, where in the previous picture I showed the true value of the proportion by the coverage rate of the interval for the single proportion. Now here there's two proportions, P1 and P2. So here by the true value of P1 and P2, here's the coverage probability. On the left I have the Wald interval. On the right I have this Agresti-CAFO interval where you add one success, one failure to each group, one to every cell in the 2 by 2 table. And you can see that you get these big kind of dips down towards 0 in the Wald interval if either of the proportions is either of the proportions is either very low or very high. You get very bad performance, and you get performance that's well below 0.95, and this shrinkage towards 0.5 for each of the means for each of the proportions, it improves things dramatically, and it's a very easy thing to do. And then here's a simple, another exact same plot, just some cross sections through it of different sorts. And in the top ones I have where P1 minus P2 equals particular values, and then on the bottom one I have ones where ratios of P1 and P2 are fixed. In other words, it's just sort of slices, maybe not slices or curves through that two-dimensional picture. And it just shows the in a nice easy 2D plot what the relative performance of the Agresti-CAFO interval is relative to the Wald interval. Okay, let's briefly go over some likelihood plots and Bayesian analysis of two binomial proportions. So likelihood analysis requires the use of profile likelihoods or some other technique to reduce the dimension down if you want to do a 1D likelihood plot. And we can actually show you later on a way you can use the so-called non-central hypergeometric distribution to get an exact likelihood plot for the odds ratio. But for the difference in the proportions, it's a little harder. Probably doing a profile likelihood would be the way to go. So it's a little hard, so let's leave that discussion for elsewhere. So instead, let's talk about being a Bayesian. So imagine, so we talked about for a single binomial proportion, putting a beta prior on a probability to get a posterior. So so imagine putting an independent beta alpha 1 beta 1 prior and a beta alpha 2 beta 2 prior on P1 and P2 respectively. Then the posterior, so remember how the calculation goes. You take likelihood times prior equals posterior. So here the likelihood is P1 to the x1, 1 minus P1 to the n1 minus x1, P2 to the y1, 1 minus P2 to the n2 minus y2. And then the beta prior is P1 to the alpha 1 minus 1, 1 minus P1 to the beta 1 minus 1, P2 to the alpha 2 minus 1, 1 minus P2 to the beta 2 minus 1. So if we multiply all those together, we get this formula right here, which exactly shows that if we have two independent binomials and then we multiply them by two independent betas, we wind up with an independent a pair of independent beta posteriors, one beta posterior for P1, one beta posterior for P2, where now the beta parameter is no longer alpha 1 but alpha 1 plus x1 for P1, and the beta parameter for P1 is n1 plus beta 1. The alpha parameter for P2 is y plus alpha 2, and the beta parameter for P2 is n2 plus beta 2. So it's basically like alpha 1 and beta 1 are the beta alpha and beta parameters for P1. A priori, after you factor in the data, you add the successes to alpha and the failures to beta. You add and the same for P2, and then you get the beta posteriors. And the easiest way to explore this posterior is with Monte Carlo simulation, and I'll show that right here. So it's very simple. So here I define my x, my n1, my alpha 1, my beta 1, my y, my n2, my alpha 2, and beta 2. And here I just did a uniform plot prior. So if I have a beta with a 1 and a 1, that's just uniform. So I put a uniform on both P1 and P2. Then I'm going to sample from the posterior. So I just simulate random betas. I simulated 1,000 beta pairs, where now my alpha parameter is x plus alpha 1, n minus x plus beta 1. And then for P2, my alpha parameter is y plus alpha 2, and n minus y plus beta 2. So imagine if I want to look at the risk difference, here the risk of side effects. P2 minus P1 is the parameter that I want, and it does. So here P1 is a bunch of posterior P1 simulations. P2 is a bunch of posterior P2 simulations. If I subtract them, R does it component by component, so I get a collection of 1,000 risk differences. I could plot the density of the risk differences in the next line. I could calculate the lower 25th and the upper 97.5th quantiles of these simulations to get a Bayesian credible interval for them. I could calculate the posterior mean, and I could calculate the posterior median. And in the next slide, you see exactly this. I have some R code called 2binom post, which which is on the GitHub repository, but also will be on the I'll put on the course website. It puts out the mean, risk difference, relative risk, and odds ratio, the median for those three, the mode for those three, and equitail confidence intervals. Boy, what I mean by equitail confidence intervals, I mean is 25% in the lower tail and 2.5% in the lower tail and 2.5% in the upper tail, which I think we discussed for the one sample binomial case. We discussed that maybe it's better to not do equitail confidence intervals, but credible intervals. But in this case, it's easy enough to do it that way. So why don't we just do it that way? And go through the 2binom post code. It's very simple to do this. And here, what I'm showing is the posterior for the risk difference. And this is what's nice about Bayesian intervals. So here, we're simulating P1 and P2 a posteriori. So we're getting the posterior joint draws from the joint posterior distribution of P1 and P2. Any function of P1 and P2 that you then want to investigate, it becomes very easy to do. And so here I took the risk difference and plotted the density. I put some blue lines where the credible interval occurs, and the red line is identically at 0. And so you can see that 0 does lie within the credible interval. But you can also see with the posterior where what points are better supported by the data for the risk difference. And even though 0 is in our credible interval, it's not a terribly well supported value in the data. I should say it's not a terribly well supported value a posteriori. Well, that's the end of the lecture. That was a whirlwind tour of risk difference style intervals for 2 binomial proportions. I'm hoping at this point that a lot of these topics in the class will start to come very easily to you because we're just kind of using the same techniques over and over again. And I look forward to seeing you for the next lecture.